Learning objectives. Sub-assembly. In this lesson, you would be learning about sub-assemblies and the following in details. Sub-assemblies, integration with electronic boards, and wire harnessing. Electronic assemblies. Electronic assemblies consist of any number of electronic and non-electronic devices. They are screws, heat sinks, carrier plates, etc. They are grouped together to perform an assembly. It is a self-contained production item. A production item is built within a particular facility. In that, each product follows its own process flow. For example, insertion mounted printed wiring board (PWB) can be built in the same facility as a surface mounted PWB. Different equipment and process. However, different equipments and processes are used. Both boards can be populated within the same pick and place machine. But solder reflow is commonly done with a wave solder system for insertion boards. The surface mount boards wider paste or thick solder plate that is reflowed in a vapor phase or infrared furnace. There can be many levels of assembly within a given system. The final system or top assembly can contain many assemblies. Each of these sub-assemblies can contain its own sub-assemblies, and so on. Most sub-assemblies are manufactured as deliverable self-contained units. They are built at various facilities. The system house obtains all of sub-assemblies and integrates them into the final system. The parts used within a system are commonly listed according to the sub-assemblies. They are set up to make up. This list starts with the final system at the top, with the major sub-assemblies as branches row. These sub-assemblies then branch out further with their own sub-assemblies and components. This listing is referred to as System Pans List. System Breakdown. Uses of sub-assemblies. The basic sub-assemblies commonly used within deliverable electronic units. The assembly processing associated with each sub-assembly has a role. It demonstrates how these sub-assemblies are grouped together to form new assemblies. Assemblies which are then used as the building blocks for larger assemblies. Finally, the integration of these assemblies to form the final system. In the example given here, each indentation indicates a lower level of assembly. The quantities given are for one assembly only. For example, there are 32 transmit modules in the radar. Each transmitter module has one module housing, one cover, one PWB assembly, and so on. Die assemblies. The simplest sub-assemblies are known for die assemblies. They consist of a bare die such as a transistor or diode, mounted on a tab having a conductive surface. These die assemblies are then mounted on top of a substrate. It is protectively overcoated in commercial applications or within a hermetically sealed package or hybrid in military applications. Reasons for building assemblies. It makes them much smaller than a discretely packaged or canned diode or transistor. Why not just mount the dies directly on the higher assembly substrate to further decrease the size needed by the dies? This is indeed the common practice used in hybrid assemblies. However, by first mounting the dies on tabs and not directly on the substrate, It is possible to test the dies functionally prior to committing them to the more expensive higher assembly. With the ability to pretest, these die assemblies are utilized for low-yield dies, such as application-specific integrated circuits, high-power dies, such as field effect transistors, FETs, or when it is essential to match pairs of dies for functional reasons. The tab allows for easier rework. When a die is determined to be inoperative, it must be replaced. To replace the die, the substrate assembly must be heated to reflow the solder or soften the epoxy with which the die is mounted. The die is then extracted from the substrate. Since most dies are only 0.010 inch thick silicon, they tend to come off in pieces. These pieces must be carefully pried off one at a time. Extreme care must be taken not to damage the neighboring components in the process. Die assemblies with the support of the tab lift up in one piece. This greatly eases the reworkability of the assembly. Die assembly materials. The tabs used for die assemblies are metallized ceramic or metal. It has been plated to allow for proper mounting and wire bonding. Metal tabs provide for the backplane of the die assembly to have the same electrical function as the backplane of the die. If a transistor is mounted to a metal tab, the tab becomes the collector, the backplane input or output. The collector in the case of a transistor can now be accessed by connecting to the backplane of the die assembly or by probing or connecting to the top of the tab. If aluminum wire bonding is used, the minimum thickness of gold that is recommended is 0.0001 inch. Ceramic tabs are employed when it is not desired to have the backplane of the die assembly active. By mounting the die on a ceramic tab, the surface metallization tab becomes the collector in the ease of our transistor. The ceramic tabs are metallized with thick film gold alloys or thin film metallization. If 96% alumina is used, the ceramic substrate is laser drilled. Snap straight. It is dividing the substrate into an array of the desired tab dimensions. This perforated substrate is called a snap straight. The thick film is printed and fired onto the snap straight in an array of bonding paths within the perforation. The snap straight is then snapped apart, forming all of the individual tabs. The backside of the snap straight may be left as bare ceramic if the die assemblies are to be dielectric epoxy mounted. It may be metallized in the same manners as the top surface to allow for solder mounting of the die assemblies. If thin film metallization is desired, alumina is used. These substrates then have a base metal such as Cr or Cu deposited on them. They are then NiAu plated in the same manner as metal tabs. After plating is completed, the substrates are diamond sawed into the desired dimensions for the tabs. BEO tabs. If BEO tabs are required to provide high thermal conductivity, they are metallized using thin film methods. Thick film does not provide good adhesion to the BEO. Die assembly processing. The dies are mounted to the tabs. It gets stuck using solder and eutectic mounting methods. Their axis of the diagram gives the composition of the alloy. The y-axis is temperature. The liquidized lines indicate the temperature at which a given composition it will completely melt or be in a liquid phase. The solidus lines indicate the temperature at which a given composition will crystallize. It will become completely solid. The areas between the liquidus and solidus lines represents the plastic zones of a given composition. The plastic zone is one in which both liquid and solid phases are present. In other words, as the temperature is increased for a given composition, the composition starts to melt. It happens when the temperature matches that of the solidus and has completely melted when the temperature matches that of the liquidus. The eutectic is the point in which the solidus and liquidus intersect. The eutectic alloy is one whose composition yields the eutectic points. Eutectic die mounting. It is the composition with the lowest melting point. It is going from solid to liquid at one temperature. Eutectic die mounting is the method of mounting die. It uses eutectic alloy as the means of attachment. Eutectic mounting can be accomplished with or without the use of solder perform. In the latter case, a silicon die is placed on the gold-plated tab. The tab in turn is placed on the hot plate of a die bonding station. Dry nitrogen is blown over the die mounting area. The entire process is done in an environmental chamber that is filled with dry nitrogen. The temperatures of the tab and die pre-brought up to approximately 400 to 420 degrees Celsius, about 20 to 40 degrees Celsius above the gold silicon eutectic points. The die is gently rubbed back and forth. It is scrubbed into the gold plating. This is done until the gold and silicon melt together to form the eutectic alloy. At this point, the die is eutectically bonded to the tab. This method is very labor intensive. Solder preform mounting. It needs a high potential for damaging the die during the scrubbing process. The most common die mounting method is here. It is to mount the die to the tab using a preform of the desired eutectic alloy. This method is referred to as eutectic mounting. It is also called solder preform mounting. The choice of an alloy depends on the metallization of the substrate, the back plane of the die on the desired free flow temperature. Other considerations include the formation of intermetallics. It can affect the long-term reliability of the unit. For example, 80% gold, 20% tin has a eutectic point of 280 degrees Celsius. This temperature is high enough. Surface mounting. The surface mounting of the substrate with eutectic lead tin, 63% lead, 37% tin, which reflows at 180 degrees Celsius. It can be done without risk of reflowing the die mounts, but it is lower than some of the other commonly used gold eutectics, thus limiting the exposed die to extreme temperature. This alloy also has good wetting properties to both gold metallization. They are commonly found on the substrate and the diffuse gold on the backplane. However, gold-tin intermetallics are readily formed at relatively low temperature. These gold-tin intermetallics are very brittle and can lead to mechanical fracture failures. Silver eutectics are not brittle, but silver cap migrates, leading to small changes in resistivity over time. Silver is also notorious for corrosion problems. Some commonly used solder alloys are shown here. Once the alloy is determined, the die can be mounted by a method similar to silver tin scrubbing method discussed earlier. However, the preform, which is punched with a cookie cutter die or simply cut out of the alloy foil with scissors. It is placed between the die and the mounting surface. Chip carrier assemblies. Chip carriers are plastic or ceramic packages. They carry a single chip or die. The assembly processes used to make chip carriers. They are very similar to those used to make dual inline packages, DIPs. They are used for plastic chip carriers or ceramic packages, SERP packs for ceramic chip carriers. Plastic chip carrier fabrication and design. The first step in fabricating a plastic chip carrier is to punch or to etch. It is done on a lead frame pattern into sheet metal. It is typically cover that has been plated with nickel and gold. The die is epoxied to the center of the lead frame. It is then wire bonded accordingly. The lead frame with die and wire bonds is then encapsulated versus in a thin plastic mold. In case of plastic chip carriers, the leads that extend of the molded body. It can have a full winged or DIP configuration. It is shaped like letter J, hence the name J-leaded chip carriers. The plastic chip carriers are always leaded. Ceramic chip carrier fabrication and design. Ceramic chip carriers are made of coke-fired ceramic and tungsten metallization. Any exposed tungsten is nickel and gold plated. The ceramic body is available in two styles. They are slam or flat pack and multi-layered with cavity for the die. The slam chip carrier can be single or multi-layered. Chip carrier assembly processing. The chip carrier processing is very simple. The die is mounted with epoxy. Sometimes it is mounted on a solder perform. The die is then wire bonded by thermocompression or thermosonically. The lid with perform is clamped now. It is done on top of the seal ring of the chip carrier. It occurs after a bakeout within a dry nitrogen. When a vacuum is created, the lid is also clamped. Then it outgasses all potential contaminants. The lid is ceramic with a metallized ring along the perimeter. It matches the seal ring on the chip carrier. Sometimes it matches with nickel and gold-plated cover with a ring-shaped solder preform tacked along its perimeter. The solder preform is eutectic gold tin. The chip carriers are with their clamped-on lids. They run through a furnace. It is programmed to reflow the gold tin solder. Now the chip carriers are removed from the furnace. Then it is tested. Applications tested. For space applications also it is tested. This testing will include burn-in. The final product is available with the nickel gold plated finish. Sometimes it is available also with a pre-tinned finish. Using TAB, tape assisted bonding. Pre-tinning involves dipping the chip carrier. It occurs into a solder pot of 60% lead solder. Dies can also be mounted inside the chip carrier. For that, tape-assisted bonding (TAB) techniques are used. Chip carriers are sometimes customized during the assembly process. In this case, a pattern of separate mounting pads is laser scribed into the cavity. This permits mounting multiple components. It occurs without sharing all the terminations. It sometimes occurs in backplanes together. The components are then mounted with epoxy. The components are now wire bonded. Finally, it's sealed as before. These customized chip carrier assemblies are referred to as chip carrier hybrids. Die mount pad. The die mount pad is the center of the slam and is surrounded by wire bond pads. These wire bond pads wire down to the buried layer. It is fan out toward the edge of the chip carrier. They extend either wire up to the top of the castellation or wire down to the solder mount pad. It moves to form castellation in the case of multi-layer design. Uses of die mount pad. On the surface of the chip carrier surrounding the wire bond pad is a ring frame of metallization. The configuration of the slam chip carrier is given here. Multi-layered ceramic chip carriers are coke-fired ceramic layers with windows cut out into the top layers. Process of layers. When these layers are fired together, the windows form a cavity. The bottom layers of the chip carrier form the bottom of the package. The next layers have small windows that form the lower cavity where the die is mounted. The third set of layers, the slightly larger window, form the wire bonding ledge. It happens within the chip carrier. The top layer has the metallization rings surrounding the window. Pin grid array packaging. Pin grid array PGA packages are high lead count chip carriers. To accommodate high lead count without increasing the perimeter of the chip carrier, the input-output is designed into an array of pads. It is kept on the bottom of the package. It is done instead single row along package perimeter. The LEDs are pedestals that are braced onto the array of pads. It yields an array of pins for insertion mounting to the PWB. Likewise, to accommodate the high input-output count, dual ledges for wire bondings are typically found inside a PGA. PGAs are available in both cavity up and cavity down configurations. Interconnection of die assembly. The interconnection of die assembly is most common. It is accomplished with wire bonds. The standard wire used is 0.0007 inch or 0.001 inch gold. For high currents, larger diameter gold wires up to 0.005 inch can be used. However, the price of gold is costly. Hence, interconnection can be costly. Therefore, we want better current carrying capacity. For that, we need to use 0.010 inch diameter aluminum wire. It can conduct current with high load than gold wire 0.001 inch. The current carrying capabilities and fusing limits of some standard size wires are given here. Gold wire bonds are made using thermocompression. The thermosonic bonding method is also done by gold wire. In both cases, the wire is fed through a capillary. Heat is applied to melt the wire. Interconnection of die assembly. Ball bonds. It is applied to form a ball of material. This happens at the end of the wire. This ball is then pressed for thermocompression bonds, or it may be scrubbed into place on the die. These bonds are called ball bonds. Thermosonic bonding arises. The latter technique involves applying heat and pressure. This process occurs while vibrating the wire at ultrasonic frequencies. Hence the term thermosonic bonding arises. The wire is then pulled through the capillary. It is looped over the bond pad on the substrate. There, the capillary presses or scrubs the wire. It makes it into the gold metallized bonding pad on the substrate. Then forms the stitch. The wire is then broken. It leaves a tail. The process shows the steps of forming a ball bond. Intermetallics. The gold, substrate metallization and aluminum wire are placed together. Then sufficient heat is applied. It is done to form gold-aluminum intermetallics. These intermetallics are very brittle. It can even weaken the process. Therefore, the bonding strength of the wire bonds gets weakened. For this reason, thermal bonding methods cannot be used. It will not help to form aluminum wire bonds. Aluminum wire bonds are formed using ultrasonic bonding techniques. Interconnection assembly. Ultrasonic techniques. Ultrasonic techniques are similar to the thermosonic technique, but it is performed at room temperature. Because no heat is applied, no ball is formed. Both ends of the wire bond are stitched. These stitches are also called wedges. The bonds are known as wedge bonds. Pull testing. It depicts the formation of a wedge bond. Military and space applications specify that they test the bonds for their purpose. The standard test is used called pull testing. This is a military standard test. Destructive test. It can be done as a sample destructive test also. This can be performed when the wires are pulled until they fade. The failure is recorded by documenting the type of failure. It may be a ball lift, break in wire loop, break at a stitch, etc. The force at which the failure occurred can also be noted. Non-destructive test. Non-destructive pull testing is used here. It pulls each wire to a specified force. If the wire bond does not break or fail, we can arrive at the conclusion that this unit passes the test. The process shows a wire bonding being pull tested. Applications. Military and space applications. It typically requires the maximum reductions in weights. The area and volume along with the highest reliability possible also are considered. Radar for a fighter jet. For example, a military electronic system might be radar for a fighter jet. This radar must have the most advanced capabilities, yet be small and lightweight. It can fit into the nose of the aircraft. Use of discrete packages is very uncommon. Because of the extra volume and weight, they impose quite well. Despite the higher cost, bare dice assemblies are commonly used. It is done through by means of meeting the sizing limitations of the system. In addition to increased packing densities, military applications have higher power densities. These higher densities often require that transistors. They need to be tested at high temperatures. Die assemblies are used in commercial products. They have high temperature environments. For example, car ignitions require the use of FET transistors. It must be capable of withstanding some extra pressures. They are the high temperature environment of the car engine. Discretely packaged FETs has the extra interfaces of the discrete package. Its mounting material cannot tolerate heat. Its board material may not bear the heat generated. It would not yield adequate heat dissipation, so it cannot maintain a proxy junction temperature during operation. Therefore, a die assembly consisting of the necessary FET eutetically mounted. It is attached to a highly thermally conductive tab. The process is helped by the use of molybdenum. This die assembly is then encapsulated. It is done with a high temperature protective overcoat. Microwave subassemblies. Microwave functionality is governed by a system. It is by mechanical design. They are also done with as much as by electrical design. The placement and orientation can affect the electromagnetic fields and devices. They are also influenced by proximity of components to one another. Thus, it can affect the functionality of the system. When operating process occurs at the frequencies associated with microwave applications, the functions get changed. RES stands for radio frequencies. At radio frequencies, signal speeds are very fast. The signal or current travel along metal surface. If the path length is too long, it can slow down the signal. For this reason, in cases where signal speed is the top priority, special care should be taken. The signal path must be shortened by reducing the resistance. Resistance can be reduced by having the signal path. It should be made of a high electrically conductive material. It can be done by using highly conductive die attached materials. It is also done by shortening the length of the paths as much as possible. The only component placement that will meet the operating rise times in some extreme cases. It is required by the design. The design is to stack the components on top of each other. The differences in resistance is displayed here. It occurs between components. They are placed side by side. Electromagnetic interference, EMI. Those stacked on top of each other gets differences. In other cases, electromagnetic interference, EMI shielding is required. To provide this shielding, metal barriers are added. It is attached to the die's assembly, or it is made with an integral part of the module housing. Just as component placement, it affects the electromagnetic fields. Therefore, does the configuration of the wire bonds. When wire bonds are formed, the wire is looped between connection points. The loop of the wire bond acts as a loop. It occurs within an inductor coil. This loop with its imposed inductance and capacitance can change the functionality of circuit design. For this reason, ribbon bonds are commonly used in microwave application. A ribbon bond does not loop up. Therefore, the ribbon does not add unwanted induction. So, the connection will not get affected. It is kept as does a wire bond. The potential inductance can be further. It happens by tackling down the ribbon along the connection path. It is done either by welding it to the track at multiple locations, or by simply tacking it down also it can be done. It will be tracked to the substrate surface with conductive epoxy. Demonstrates the induced inductance. It occurs between wire bonds and ribbon bonds. The ribbon is connected to the die and substrate metallization by split welding. In this process, a welding tip that is split in half. They are placed with one tip at each end of the width of the ribbon. Working principle. Power is applied now. Then the ribbon is welded across its width. It elongates to the surface metallization. It is well shown in the picture. Microwave subassemblies are highly customized. They are unique to the electrical requirements of the device. They will be utilized in such special device. Uses. Elementary subassemblies are used when area restrictions are critical. It is also used when special pretesting is required. They are typically used in military and space equipment. They are specially utilized for avionics or satellite applications. The weight and size of the system in avionics are utmost importance. Sub-assemblies in TV, computers and PCB. Televisions combine both electronic sub-assemblies and an optical sub-assembly in the manufacturing process. Computers have custom sub-assemblies unique to their application. In a computer sub-assembly, multiple electronic sub-assemblies are merged together. It is done to form the Central Processing Unit or CPU. CPU. The CPU is the actual part of the computer that runs the machine. It contains the memory, processing and sound sub-assemblies. They are usually made up of several PCBs. Each PCB may contain hundreds of components. They are attached to the PCB using solder. PCB. The PCB is then mated with other PCBs to form a part of the computer. It is responsible for specific function. Once all of the manufacturing is complete, the PCBs are inserted into a case. It forms the computer. Once all of the manufacturing is complete, the PCBs are inserted into a case which forms the computer. Optical subassemblies. The optical subassembly manages the display. It contains liquid crystal display. It is also known as LCD or plasma. Optical subassemblies are also part of cameras. They are also present in projection equipment and theater lighting. Uses. Optical subassemblies are ideally used in manufacturing. It is also used for connecting various electronic equipment. They are robotics, medical equipments, printing and publishing. Electronic devices and subassemblies. Electronic devices such as cell phones or televisions also have electronic subassemblies. The display and PCB for portable media player and cell phones also have subassemblies. They are much smaller than the ones in a microwave. They work in a similar manner. Cell phones and subassembly gadgets. Cell phones have additional radio frequency. It is also called RF. The components that allow them to pick up cell tower signals. The components are then mated with the outside housing. This is to complete the gadget. Hybrid. A hybrid microelectronic is often referred to as just a hybrid. It is a combination of more electronic components mounted and interconnected via substrate. The substrate is made of a dielectric material that is patterned with the metallized signals or tracks. The hybrid is a customized electronic function. It is packaged as a single device. Different names. Hybrid are known by many names. It includes multi-circuit package and multi-chip package (MCP). It also includes multi-circuit hybrid package and power hybrid package for hybrids with power densities. It is greater than 10 W by square inch. Some microwave hybrids are also known as integrated microwave assemblies (IMAO). However, it is important to remember that IMA is the name. It is used for any microwave assembly, in the sense that all microwave hybrids are IMAs, but not all IMAs are hybrids. From all the names just given, it can be discerned. The essential definition of a hybrid is that it contains multiple components. Hybrid design. A hybrid differs from a PWB assembly. All the components are packaged together in a single hermetic case. Unlike PWBs, in which all components are individually packaged and then mounted to the board, hybrids use bare, unpackaged dies. In other words, a given schematic with a parts list to define the components needed can be built with individually packaged. It can be leaded components mounted on an organic PWB. It provides the necessary routing between all individual components. The same device can be built using bare dies and chip components. Examples: capacitors and thick film resistors. They are all mounted to a multi-layer ceramic substrate. The substrate provides all of the internal routing. The substrate assembly is then mounted inside a metal package that is hermetically sealed and forms the hybrid. A hybrid can be as simple as mounting two diodes into one chip carrier. It can be as complicated as multiple channel amplifier. Analog to digital converter. It can be a regulator or analog to digital converter. Hybrids can be digital or analog or a combination of both. The most common bare dies and chip components mounted on a multi-layer ceramic substrate. This substrate is designed and fabricated in much the same manner as in mount boards. A hybrid substrate is typically 96% alumina with thick film metallization. Uses. However, green tape, co-fired ceramic, and thin film multilayering using polyimide as dielectrical material may be employed depending on the particular requirements of the design. The main difference from a surface-mounted board is that bare dies, not individually packaged, are mounted. It is necessary to package and or seal the substrate assembly. This setup is to provide necessary protection to the bare dies. The substrate assembly is either mounted inside a leaded case or encapsulated within a protective overcoat. Advantages of hybrid assembly. The advantages of hybrids are the vast reduction of volume, area and weight, improved thermal management, increased functional densities, increased frequency capabilities, and improved electrical performance. Disadvantages of hybrid assembly. The disadvantages of hybrid assembly are the increased cost over that of an equivalent PWB assembly. The elimination of the individual packaging of the components is the most obvious contribution to the size reduction. By this elimination, the bare dies can be mounted onto the substrate. The component placement is much closer and interconnection between the components is more direct. Instead of wire bonding from the bare die to the die packages in internal LEDs and having the signal travel through the feed-through to the external LEDs. Hybrid microelectronic assembly. It has to be soldered to connect to PWB. It then routes the signal to the solder joint of another packaged die, etc. The bare die on hybrid can be wire bonded to the substrate, which directly connects to the wire bond pad of the other die in question. Thus, electrical performance and frequencies are improved. Likewise, thermal interfaces are eliminated. Organic PWB. On an organic PWB, the heat must travel from the die through the die attaching media. It travels through the die's package and the packaged LEDs through the solder. It moves and then finally through the PWB to some heat sink. In a hybrid, the TOT travels from the die through the die attaching material. It then moves to the substrate and through the hybrid case to the heat sink. Not only is the number of thermal interfaces reduced, but also the thermal conductivities of the materials used in the hybrid are higher. It is capable of dissipating more heat. Thus, thermal management is improved. Uses. The disadvantage of using hybrid is the increase in cost. It also involves in turnaround time or the time it takes to go from electrical design to finished product. Organic PWBs use polyimide with copper metallization. Hybrids utilize ceramics with gold. It is also used with silver or gold alloy metallization, all of which are higher in cost. Dies, whether discrete such as diodes and transistors or integrated circuits. It can be purchased in two forms. One is already packaged or bare. Packaged dies come in many varieties. They range from leadless chip carriers, LCCs, for surface mounting. Dies are designed for mounting on PWBs. All of these packaged dies are designed for mounting on PWBs. The suppliers package the dies and then test them to sort them. For example, in the case of a diode, all the bare dies are probed while still in wafer form. This probe or test indicates only that the dies act like diodes or do not work at all. This type of testing is often referred to as a go, no-go test. All diodes that pass the go, no-go test are packaged. After being packaged, the diodes are fully tested under full power and operating conditions. They are then sorted into bins. Example, there might be 3 different bins for a particular diode. Bin 1 for diodes that operate only under 3V, bin 2 for V and bin 3 for 7 to 12V. These units can even be fully screened by the military standards. It includes burn-in to weed out any infant failures. Packaged dies. Packaged dies are in greater demand than bare dies and are manufactured in very large quantities using automated techniques. Therefore, the cost of these packaged units only pennies, more than that of the bare dies. In some cases, the cost of purchasing bare dies is even higher than that of their packaged counterparts. It is because of the increase in handling difficulties, the electrostatic discharge (ESD) damage and decreased yields associated with the bare dies. Testing. It cannot be completely tested and screened prior to packaging. For some ICs, those utilized in microwave applications, packaging increases yield due to the EMI and ESD protection the packaging offers. Bare dies are more susceptible to damage than their packaged counterparts. Their surface metallization can be scratched or contaminated, damaged by FSD, and shipped when picked up by the tweezers. They can simply be lost because of their tiny size. Example, a transistor can be as small as 0.011 into 0.077 inches. High post mounted. The packaged dies have high post mounted yields, typically over 98%. Bare dies have lower post mounted yields because of their vulnerability to damage during the mounting process. Bare die yields can be as low as 60% depending on the complexity, sensitivity, and process control used in their mounting. Typically, under proper conditions, a bare die yield 90 to 97% can be expected. The yield of a PWB assembly is normally quite high. It is because all elements and components used in the assembly are fully tested prior to commitment to the PWB. Hybrids, however, use the bare dies, which have lower yields. Hybrids utilize several bare dies, thus compounding the overall yield problem of the end product. If a hybrid uses 12 diodes, each with an expected yield of 95%, what is the best available yield of the hybrid? The yield of the hybrid would be 0.95 square 12, which is equal to 54%. The yield of the hybrid would be 0.54 or 54%. Hybrids can also be more costly. It is in terms of time to design. As with PWBs, the layout and routing are done on the computer. Once this layout has been checked, the information from the design station is downloaded. It will be allowed into a laser artwork generator. The LAG draws out the layers on the fill, example, mylar. For a PWB, this artwork is used to pattern the metal on the board. For hybrids, this artwork must first be reduced in scale. It is then converted into screens and stencils. Then it will be used to pattern the metallization onto the substrate one to one. Hybrids mounted. After board fabrication, the PWB can be assembled. It can be done by mounting components and reflowing the solder. Hybrids must have the components mounted and wire bonded. The substrate assembly must then be packaged. Thus, hybrids can be more labor intensive than PWBs. Lead time, the time it takes to order and receive components, is typically longer for hybrids. Since hybrids are used only when size limitations are extreme, they are typically not a high volume production item. For this reason, hybrid piece parts such as bare die and chip components are not in as much demand. Thus, component costs and delivery times are often greater. Component mounting. The most common method used for mounting the components on the substrate is to attach them with epoxy. In the 1960s and 1970s, dielectric, that is, non-conductive epoxies used. However, with advances in polymer engineering, the adhesion of epoxies was greatly improved, along with techniques for filling the epoxies with metals to make them electrically conductive. To obtain a low enough resistance to allow for proper conduction, the epoxies must be 70 to 80% metal. The metals used for filling the epoxies are gold and silver. Copper, although an excellent electrical conductor, is not typically used because of its highly corrosive characteristics. Metals other than those mentioned are either non-conductive enough, too expensive, or not conducive to filling. Gold and silver's lower resistivity. Because of the price of gold and silver's lower resistivity, silver is the material commonly used to fill epoxies. In recent years, there has been much controversies over the use of silver-filled epoxies in military application. It was feared that the silver in the epoxies would oxidize and thus greatly reduce the conductivity of the material with time. It has also been feared that the silver would migrate over long periods of time, collecting in one area of the epoxy joints. As the silver migrates, the area it migrates away from forms an insulating layer. Data showing changes in resistance of the epoxy over time would seem to support these two fears. However, more recent studies have shown that if the epoxy is properly processed and is contained in a hermetic environment, these changes in resistance over time are insignificant. The theory is that if potential contaminants and oxidizing agents such as air and moisture are kept away from the epoxy, the silver cannot oxidize and its resistance is not greatly affected. Silver migration still occurs, but its effect is small and noticeable only over a very long period of time or at very high frequencies. The organics within the epoxies can spoil if not properly stored. Care must be taken to maintain the integrity of the material. Premixed epoxies must be kept frozen or refrigerated. The shelf life of epoxy kept frozen is 1 year, refrigerated is 6 months, and stored at room temperature is 1 to 3 months. When the epoxy is to be used, it must be taken out of the freezer and allowed to thaw before opening the container. If the container is opened before the material reaches the room temperature, humidity in the air can condense the material and contaminate. Further protection of the material must be employed. Only clean stainless steel utensils should be used to mix and apply epoxy. Wood depressors can leave wood fibers that can react with epoxy organics. Old material left on the screen after printing should never be mixed back with the fresh epoxy. This material should be gathered in its own container and recertified prior to use on deliverable product or set aside for engineering or prototyping use only. If the device is mounted with conductive epoxy, the epoxy acts as the electrical connection. For example, a chip capacitor mounted with conductive epoxy is mounted with the epoxy only under the two end terminations. No epoxy is under the body of the capacitor, for it would cause a shock. In high current or microwave applications, the resistivity of the conductivity epoxy or the minute changes of resistance over time due to silver migration do not meet the electrical performance criteria of the design. The capacitors are mounted with dielectric epoxy under the entire length of the capacitor body, and the end of terminations are wire bonded to provide the electrical connection. Both epoxies, dielectrics and conductive, employ the same component mounting techniques. Epoxy. Epoxy can be applied as either a film or a paste. Epoxy films can contain fiberglass mesh support as found in the pre-peg or B stage used to laminate the layers of an organic PWB. Epoxy films can also be formed by printing a layer of epoxy on a non-stick inert surface, example mylar tape, and partially curing it. This partial cure leaves it flexible but no longer fluid. Film adhesives can be purchased as sheets of approximately 12 by 12 inches or performed by cutting or punching into the desired size. Film adhesive come in thickness from 0.003 to 0.012 inches. Most film adhesives require the application of pressure during the cure cycle. Film adhesives are used for mounting large area devices. Example, mounting LCCs approximately 0.300 in square to larger die assemblies or chip carriers with higher input-output counts. Uses. Film adhesives are also used for mounting the substrates to the case floor, or mounting the case to the PWB, or attaching the cold plate to the module housing. Example, areas that exceed 10 in square. Epoxy spacers can be hand applied using stainless steel spatula or dental picks. Wooden utensils should never be used with epoxies, as the wood fibers can contaminate the material. Hand application is normally done only when building prototypes. Automatic dispensing is used to push the epoxy out. In a manual dispenser, the operator controls the pressure by a trigger or foot pedal. In more advanced equipment, a set pressure pulse is automatically applied amounts of epoxy. The most commonly used method for epoxy application is to print the epoxy. The epoxy is screen printed in the same manner as a thick film paste is screen printed. The differences are that a large mesh, typically 80 count, and a thicker emulsion 0.002 to 0.010 inches is used. The larger mesh is needed to accommodate the epoxy's larger particle size and higher viscosity. The thicker emulsion is used to obtain the thickness of epoxy deposit needed. Stencil printing can also be used with solder paste printing. Advantages. Advantages of stencils will be discussed later in surface mounting. Other component mounting methods use solders. As discussed earlier, under die assembly processing, the die can be scrubbed down by using eutectic alloy formation between the die and the substrate metallization, or by using eutectic solder alloys performs. Furnace mounting with the use of eutectic alloy preforms is another process used with hybrid. Chip components can also be mounted using solder paste or solder wire. The solders used for these applications are not always eutectic, although they can be. These solders are normally lead, tin alloys, rather than gold alloys used for die attaching. These solders reflow at lower temperatures and are not necessarily eutectic, that is, do not have a single reflow temperature. To get good uniform adhesion or wetting of the solder to the surface metal, oxides must be removed. Removal of oxides can be accomplished in two ways. In one method, the solder is reflowed in a reducing atmosphere in a furnace filled with foaming gas. Foaming gas is a mixture of inert nitrogen and approximately 5% hydrogen. The nitrogen prevents the introduction of any new oxides, and the hydrogen, at the reflow temperature, reduces the oxides that have formed on the solder. This method is normally used for high temperature or eutectic solders. The other method is to utilize flux to increase the wetting of the material. The flux chemically reduces any oxides on the metal surface or in the solder. Flux can be applied to the metal surface or on the component prior to mounting. For example, flux can be printed on a board that has been pre-tinned or has been thick solder plated. The flux can then act as the tacky substance that temporarily holds the components in place prior to solder reflow. Another means of introducing the flux is to dip the already pre-tinned components into flux before placing them down on board surface. This method, however, is labor-intensive and not frequently used. Solder paste and most solder wires have flux in them. Solder pastes have particles of the solder alloy suspended in a solution containing the flux, emulsifiers, and volatile solvents which burn off during the reflow. Solder wires have a rosin core that contains the flux. Solder paste. Solder paste or wire can be reflowed by applying heat locally with soldering wand, sometimes called a soldering gun or a hot air gun. Solder paste can be applied to the substrate by hand or by a screening method. The components are then placed in the paste and the solder is reflowed. The reflowing of the solder paste can be accomplished by a variety of methods. As already mentioned, the paste can be reflowed locally, or the entire substrate can be submitted to the heating cycle needed to reflow the paste. Reflow of solder can be accomplished by placing the substrate on top of a hot plate or on a belt reflow system. The latter system has a belt that travels down the length of the reflow equipment through heated zones. Zones heated. Zones are heated conductively by heating coils under the belt and or convectively by hot air or nitrogen blown down on top of the belt. Furnace reflow can involve fluxless solder reflow, as utilized in eutectic die attach or fluxed solder. In case of the fluxed solder, the reflow is performed in a nitrogen atmosphere. A reducing atmosphere is not needed because the flux provides the reducing or wetting agents. Another furnace reflow method is to provide the energy needed to reflow the solder by exposing the substrate within the furnace infrared radiation, hence the name IR furnace. Finally, solder can be reflowed by a vapor phase. In this case, the substrate is lowered into a chamber filled with the vapor of a freon. The freon and its boiling point determine the temperature of the vapor. Solder. A part is lowered into the vapor, the both surface, and thus the solder paste is exposed to the temperature of the vapor. The solder is reflowed as the vapor condenses on surface of the substrate and transfers its latent energy of the condensation to the solder. Whenever these methods are used, the substrates must be defluxed or cleaned prior to mounting any bare dies. It is best to deflux the unit before it has a chance to cool down fully. In the cool down process, the flux is baked onto the board and penetrates into the surface of the board. If cleaning is conducted while board is still warm, that is, while the flux is still tacky prior to baking on the flux residue left on the board will be minimized. Any flux residue left on the board can outgas later and damage the bare die. Bare die cannot be mounted using methods involving flux because of the damage the flux does to them. Even though the dies are passivated or given a protective overcoat of a glass or an oxide, this passivation is performed at the wafer level. When the wafer is sawed into the individual dies, the passivation is also cut. Thus, only the surface of the dies, not the sides, is protected. The flux and flux fumes can deposit on the dies and migrate under the passivation at the sides of the dies. The flux can then attack the oxides and metallization of the die, causing loss of functionality over time as the flux eats away the IC layers. Conclusion. Subassembly. Thus, we have learnt about subassemblies and the following in details. Subassemblies, integration with electronic boards, and wire harnessing.